All right. I welcome you in this course of coordination chemistry, and this is going to be the very first class. So here, let us start this course with the bonding theories. Okay. I'm sure that you have gone through the syllabus of this course, and first we have to discuss in the first unit we have the bonding theories. And here, not only that valence bond theory and crystal field theory, we will also have a good discussion on the molecular orbital theory. Uh, After that, you will see how these theories can explain various properties of transition metal complexes. Okay. Uh, Once we have done that task, which will take, I'm sure, the first 7 8 lectures, after that, we will be discussing in brief how do you find out the stability constants experimentally. More focused on experimentally. Theoretically, you are aware with the what is the stability constant of transition metal complexes. I will just briefly give you that how people determine it uh, experimentally. Okay. After that, we will be again coming back to the bonding theories, but in this case, that how these theories will be helpful in explaining the spectra. And here in the spectra, we will be discussing in more details that how different spectroscopic states that we arrive to. Okay, how do you find out the ground state? How do you actually get the number of transitions? Okay, all those exercise you will do, and finally we'll be coming to yes. After that, we will be discussing the magnetism in details, how the magnetic properties of different magnetic behaviors of transition metal complexes they display. Okay, and after that, again, we are going to have the a good discussion on the reactions of the transition metal complexes. Okay, so this is more or less this is the syllabus that we have. Okay, that I will be sharing the syllabus separately with you. But in that for today's presentation, let me just open the slides on the transition metal complexes bonding theories. So just give me a minute. All right. I hope you can see the slides. Let me make it in full screen mode. All right. So here, first unit, bonding theory in transition metal complexes. Well, I am sure in your graduation and your previous classes, you have actually gone through the basic theory of transition metal complexes. That is the basically Werner's theory, Valence Bond theory, and I am sure to some extent you also have studied the crystal field theory. Okay, I would like to take this introductory class to repeat a few things over here. So I would start with very basic concepts, so you don't have to, again go through all these things once again. So basically, we are discussing here the coordination complexes or the metal complexes. Okay, so how do you get a metal complex? Very simple. You have metal and ligands bind to metal ions, and metal plus ligand is something that results into formation of metal complexes. Okay, there are so many metal ions, there are so many ligands, right? And you can see just like the 26 alphabets in the English, right? They can give such a huge vocabulary. So many different words can be created. Similarly, taking this number of ligands and metal ions, right? We can have a large number of metal complexes. All right. These metal complexes, they display many different type of properties. Okay, so you know what are the metal ions. Metal ions are, you can see, although these are also S block also metal ion, but we are talking about transition metal ions over here. So that is these three series, scandium to zinc, and zinc also we consider over here because zinc complexes have very similar properties to the other transition metal complexes, and so it's good to study them together. From gallium to the cadmium, then lutetium to mercury. Okay, in between over here, okay, you know that the F block elements are there, right? So F block elements are called inner transition elements, but basically they are also our transition elements, right? And their metal complexes are also relevant as far as the studies of coordination complexes are concerned. All right. So I told you that M plus L form ML, and this L could be any number depending on what is the coordination number that is preferred by a particular metal ion. This M here is called as central atom in the proper language of coordination chemistry. So the central atom we can define is the atom in a coordination entity. So we need to know what is coordination entity, which binds other atoms or groups of atoms, that is called ligands, to itself, thereby occupying a central position in the coordination entity, right? This coordination entity terms came twice here. So what is coordination entity? The central atom in, let's say, an ICl2H2O4 here, cobalt hexamine complex or platinum Cl4 2 minus complex. The central atom in these coordination entity, this as such, this is called a coordination entity, right? So these nickel, cobalt, platinum are the central atom in these examples, and coordination entity is this entire thing which is inside the this square bracket. Okay. Generally a transition metal complex is enclosed in square bracket, whether it is neutral or positively charged or negatively charged in matter. A coordination entity should be enclosed in a square bracket. Okay, so this is the basic terminology. I'm sure that you know what is a ligand. Ligands are nothing but neutral molecules or ions having a long electron pair that can be used to form a bond with a metal ion. That is the simplest definition that we can give for a ligand. Monodentate ligand are the one which can form only one bond with a metal. Water, ammonia, carbon monoxide, okay, chloride, bromide, iodide, or cyanide. They form one bond at a time with the metal. Although you can see like say thiocyanate, either a nitrogen can coordinate or sulfur can coordinate, but at one point of time they will coordinate in a monodentate fashion. So these are basically the monodentate ligand. Then you have bi and polydentate ligand. So these are the examples of polydentate ligand. Some of these ligands like EDTA, ethylene diamine, oxalate are very very common. And then we have some uncommon ligands too. Okay, but there are enormous number of ligands like pyridylamine based, phenol based ligands are there. Okay, they exhibit a very interesting coordination chemistry. So it's good to know all these things in our mind that what exactly that we are talking about, what is metline, what is ligands, right? If somebody asks you to draw the structure of some ligands, you should be ready with some of the ligands. Sometimes I have noticed that the student, if you ask them simple things, although they know it, they are not able to express it properly. So you should be practicing it. All right. As I told you, the coordination entity is basically, you can see, a coordination compound is any compound that contains a coordination entity. A coordination entity is an ion or neutral molecule that is composed of a central atom, usually that of a metal, to which attached a surrounding array of other atoms or groups of atoms, each of which called a ligand. Again, everything is defined here again. Classically, a ligand was said to satisfy either a secondary or a primary valency of a central atom, and the sum of these valencies were called coordination number. For example, in the cobalt hexamine complex, coordination number of cobalt is 6. And for the in this complex, the platinum tetrachloride, coordination number of platinum is 4. Here it is. Okay, it's a complex structure. You have to see the structure, then only you can tell what is the coordination number. Okay, so a coordination entity is enclosed in the square bracket, whether it is charged or uncharged. Okay, it doesn't matter whether it is charged or uncharged, it has to be enclosed in the square bracket. All right, very basic terminology. Another one is coordination polyhedra. I'm very sure that you are aware with this. It is a standard practice to regard the ligands atoms directly attached to the central atom as defining a coordination polyhedra or polygon about the central atom. The cobalt hexamine is an octahedral ion, right? This is octahedral, right? Why it is called octa? Octa represent 8 because there are like this kind of triangle faces are 8 of them are there. Okay, but you know that coordination number in octahedral is 6 because coordination number is basically like here In such case, the coordinate number will be equal to the number of vertices. What is vertices? Let's say this ligand, like this is your ligand and this ligand, they are meeting here. At this point, you can see this is vertices. There are six of them, so that is why it is coordinate number is six. Okay, so this vertices sometimes may not be true if you are having the organometallic complexity like ferrocene or so, in which the contagious atoms are coordinating. Okay, but I am sure that you can understand that square planar coordination polygon or tetrahedron, they are very common ones that we will be using a lot in this course. Geometries could be linear, square planar, tetrahedral, octahedral, or there are so many others, trigonal, bipyramidal, or square pyramidal, right? There are so many geometries that are there, which we will be discussing over the course of like next many lectures. Okay. Nomenclature, although it's not part of your, the syllabus over here, but in the first class, I just take it, and especially one kappa convention is that which I would like to make you familiar with. Okay. So in general, what is the nomenclature? What are the general rules? Please do not forget uh, sequence of ligands and central atoms within names. There are some name rules for that. Ligand names are listed before the name of the central atom. Right? Central atom is listed in the last, and ligand names are listed before that, and no space are left between part of the names that refer to the same coordination entity. Okay, no space will be left. Ligand names are listed in alphabetical order. Okay, multiplicative prefixes indicating the number of ligands are not considered. Like say, if it is let's say uh, dichloride, so that D will not be used in the this alphabetical order. The use of abbreviation in name is discouraged. You don't have to use the like say ethylene diamine. Don't use B. Write the full name. Okay, for example, cobalt Cl is pentamine pentamine because A is the alphabet that is considered over here. It is bold over here. P is not considered because penta will be indicating number. It's not. Name of the ligand is used for this, determining the alphabetical order. Then chloride, the C is there, then cobalt. So you can see there is no space in between these. That is the one mistake that most of the students make. They will start giving spaces. Okay, that is not given over. Pentamine, chloride, cobalt, chloride. There is a space here, of course, because this is the coordinate entity and this is outside chloride. We can see this is the tetragenon genonido because this is a negative charge on the genon gold. This is a gold complex. Genon is acting here as a ligand, quite uncommon maybe for you people, but some of the examples are there, and 2 plus charge is there, right? Anyway, so nowadays this like say Cl minus is chlorido, not the chloro, or Cl minus is cyanido, or hydrido H minus, right? So these are the terminology generally are used. You can make yourself familiar with these things. After the masters, you might have to teach, so it's good to be aware with the latest rules and regulations. Okay. Some other examples are given. I told you that, let's say, for example, K for FeCN6, potassium. After potassium, you can give a space because then you are starting the coordination entity. Inside the coordination entity, you don't give any space between the letters. So hexacyanidopherate 2 or potassium hexacyanidopherate 4 minus or tetrapotassium space hexacyanidopherate. All three are correct. Technically, all three are correct. Either one is fine. If you can easily find out the oxidation state, you can write the Roman numeral after the name of the metal. And or if you cannot, if you cannot, that if you cannot, if you cannot, I'm in a class. If you cannot find out the oxidation state, if you cannot find out the oxidation state, then in that case, it's okay to write the charge. So this is K4, that is 4 minus charge. All right. And then other ligands are here, the one that COCl NH34NO2, right? Just look at this carefully. Tetraamine, of course, because alphabetically amine will come first. Chlorido, and then nitrito, kappa N, because nitro is coordinating here using nitrogen atom, although it can use oxygen also. But here, since it is coordinating with nitrogen, this kappa is basically nothing but showing as a coordination. Okay, kappa N. Okay, so the coordination of which atom? Whenever there is a possibility of coordinating with different atoms in a ligand, it's good to use kappa convention. Okay, I'm sure no confusion here. Platinum Cl chlorine, Cl NH2amine, NH3. You can see diamine, chlorido here, methane amine, right? Neutral ligand, platinum, and 2. Right? Because this is neutral, Cl minus, and this is Cl minus. Or if you find out the oxidation state, it is plus 2, so you can write a platinum 2. All right. Here again says nitro is there. Again you can use a kappa N convention. Sometimes this kappa convention is very helpful to us in writing some complex names. Like for example, I generally discuss this example. If you would like to write the name of this complex, then how should we write it? How are you going to write it? Though the trick here or the key is that you write the name of the ligand first. If you are familiar with how to write the name of the complex ligands as per IUPAC rule, it will be easy for you to write the name of the complex also. Alright. So here you can see N prime bis 2 amino ethyl ethane 1,2 diamine, right? What is this N prime, right? These are the two nitrogen atoms which are bearing the 2 amino ethyl group. This is the 2 amino ethyl group, this group or this group. So these are the N prime. These are the two nitrogens that we are talking about. N prime, right? It's on the ethane. Ethane is here, right? And both of them are bearing 1,2 amino ethyl groups. So it's a simple N prime. This 2 amino ethyl ethane 1,2 diamine symmetric ligand. Okay. If you notice here carefully, it is not binding in a symmetric fashion. This 2 amino ethyl group is coordinating while this 2 amino ethyl group is not coordinating. Writing a simple name for this, right, will be very difficult. So kappa convention is required. Here you can see N 2 amino kappa N ethyl. So this amino group of this 2 amino ethyl group, one is coordinating. So this is here what we are talking about is this nitrogen N 2 amino ethyl group. This 2 amino ethyl group. This nitrogen is coordinating. So kappa N ethyl. Okay. Then you have N prime, this N prime, this is bearing this group, 2 amino ethyl. It's not coordinating, so let's not use any kappa over here. N prime, 2 amino ethyl. Then you have ethane 1,2 diamine. This is the ethane 1,2 diamine. Both these nitrogens are coordinating to the platinum, right? So you can use kappa 2. 2 means there are two of them are coordinating. N, which are 2 and N prime. So ethane 1,2 diamine, kappa 2 and N prime, chlorido platinum 2. Right? It's very simple. If you look it carefully, it's not very complicated if you actually use the kappa convention. Another one you can see in this case, this N prime is not coordinating. However, both the two amino ethyl groups are coordinating. This such kind of ligands are called flexidentate ligands. Okay, so what is flexidentate? There are multiple ways it can coordinate. Okay, there are let's say 3 or 4 or 5 uh, atoms are there in the ligand. Sometimes 3 are used, sometimes 4 are used, sometimes all of them may not be used. This is called flexidentate in nature. All right. So here N prime, right? N prime bis. This is we are talking about the 2 amino ethyl group here. Both are coordinating. So N prime bis 2 amino kappa N ethyl, right? Bis is taking care of both of these groups. Both are coordinating for 2 amino kappa N ethyl. Ethane, right? This ethane group we are talking about. This ethane 1,2 diamine, kappa N. This N is coordinating, right? N prime is not, so only kappa N and chlorido platinum 2. It's simple as that. All right, it's good to go through this nomenclature because these are the latest one. The UPSC recommendations made in 2005. If you just type this in Google, you'll find a red book. That red book has all the different chapters on the UPSC nomenclature. I suggest that you can go through that in detail. Now, after that introduction, we can come to the major bonding theories. Okay, what are the major bonding theories? I told you this is Werner's theory, Valence Bond theory, crystal field theory, of course, and molecular orbital theory. And we'll be discussing all four in the next whatever lectures it will take. All right, why do we need these theories? So many theories. Why do we need? Why just not one? Okay, we need to because we know that transition metal complexes they have so many properties, right? What are those properties? Their geometry, number of bonds, their shape, the color, magnetic properties, spectra, structure, stability, reactivity, high spin and low spin nature, splitting of the orbitals, effect of ligand types, right? So many things are there that we need to understand. Okay, in order to understand all these, we need some theories, right? Because based on that, based on the theory, we can make a better or newer complex of a desired property, right? That is the use of the theories. That you understood the properties of the certain complexes, and now you would like to uh, redesign a new metal complex with some desired property, and that is where the theory is being basically learning from the lessons of the past, right? Then you can design better of desired property transition complex, right? For many properties, because transition complexes have lot of reactivity, catalytic property, so many interesting applications are there, right? Medicinal applications are there. So you can design metal complex with desired property. Make that's why understanding theories is very important. All right. So I briefly will mention the Werner's theory. Okay. In the Werner theory, right? All of you are familiar with Alfred Werner. This is what is taught to us in 10 plus 2, right? Because around the end of last century, last to last basically, okay, uh, the Valence bonding and geometry in metal amine complex, especially such as cobalt hexamine, was a subject of immense interest. Because these complexes, there were various isomers were being formed, they were having different color, and people were not knowing what they are. That's why the name complex also came, actually. And this was a subject of basically immense interest. Some people were taking, like Alfred Werner, one of them. He was taking a lot of interest in this subject. In fact, he was taking so much interest that I can just read a part of this sentence that yes, he was a son of a factory worker, and at the age of 18, he started his chemistry research. So that tells that how much interested he was in explaining this, the properties of transition metal complexes. Well, and he won Nobel Prize in Chemistry in 1913 for his work on the coordination compounds, which he performed as a graduate student and first presented at the age of 26. So basically, he completed this work at very young age, right? And Werner was so obsessed with solving the riddle of the structure of coordination compounds, and that his brain continued to work on the problem even while he was asleep, right? So this is in general for the students that see when you are interested in solving a problem or when you are really interested in understanding something. If you take a lot of interest, you can do it. Warner was a good example. Okay, I would like to just remind you once that what was the work that exactly what was the work that was done by the uh, Werner, Alfred Werner, right? Alfred Werner made a couple of series, like platinum series, cobalt series of complexes. Like for example, in the platinum series, he isolated these five complexes of different color and different properties. Okay, first he performed conductivity. Conductivity we performed even today. If you come to the lab, right, we'll ask you that you check the conductivity of a particular metal complex or salt to find out how many number of ions are there. Right? If there is no conductivity, that means there is no ion. However, the conductivity is coming in the omniverse around, let's say, 100. We say there are two ions. If there are around 300, that means three ions, or 400 around four ions. If 500, that means around five ions are there. Number of ions per formula unit. Right? So that was one of the experiment that conductivity experiment was done by Alfred Werner, And second experiment was gravimetric estimation of how many chloride ions are precipitated out. Right? I'm sure that you know the methods of gravimetry in which you estimate the amount basically by measuring the weight of substance. So here by like you added some silver nitrate and whatever silver chloride was precipitated that was weighed, and it was found that in this case when the formula is this, the 4Cl minus was precipitated out. So 4 AgCl molecules were formed, or 3 or 2 or 1, or no AgCl molecule was formed. Based on this data, Werner was smart enough to understand that actually this is the composition of each molecules. Platinum hexamine 4 Cl4. So there are 4 chloride ion outside and 1 cation. So 4 plus 1, 5 ions are there. That's what the first 5 ions in the first molecule. Then platinum has 3 5 Cl and Cl 3 Cl outside, 3 plus charge. So if you have 3 plus 1, 1 cation. Cation is only 1, charge is only 3 plus, right? So there are 4 ions here, and there are 3 chloride ions are precipitating out. You can see over here. Only the chloride ions which are outside the coordination entity, only they are accessible. So they can be precipitated out as AgCl. Well, it was fairly easy to understand that this is what the composition is. In fact, these two experiments give a very nice information. According to Werner's theory at that time, he said that he postulated that metal ions have two different kinds of valence. One is primary valence, that is oxidation state, like say platinum, 4 plus over here. This is the primary valence, correspond to the positive charge on the metal ion. And secondary valence, that is the total number of ligands bound to metal ion. That is, let's say 6 in all these cases, right? That is yes, coordination number is secondary valence. That's how Werner at that time he defined. Nowadays, the secondary valence is commonly known as coordination number, right? And primary valence is commonly known as charge on the metal ion or the oxidation state of the metal, right? So that was a great source of information, that what Werner provided, and it kind of you can by just getting this two data immediately in your mind you have a composition of metal ion, metal complex, what exactly this may be looking like. Okay, but Werner did not stop here only. He, in fact, when he was studying this kind of complexes like platinum tetramine Cl2, which is basically nothing but an Ma4B2 type complex, he could isolate only two isomers. He tried it out, he could get only two isomers. However, if you see that when the coordination number is 6, theoretically, there are three isomers are possible. One is hexagon, one is trigonal prism, one is three structures are possible. Okay, so which structure is true? That was the question. So three possible geometries are possible: hexagon, trigonal prism, and octahedron. If you just see carefully, in first two cases, hexagon and trigonal prism, there are three isomers are possible. Okay, for this kind of complex. However, in case of octahedron, this is the only geometry where only two isomers are possible, and that's what Werner was able to isolate also. Based on that, Werner, no, Alfred Werner, he told that the geometry of this complex is actually octahedral, because in octahedral there are two isomers, and that's what you are isolating, right? It was a great source of information, like you can isolate, you can not only tell the composition but also the geometry of a complex just by getting this data, right? So that was at that time when people were knowing nothing about these complexes, it was a great information that Werner provided actually. That is the reason that he was awarded with the Nobel Prize of this work. Okay, if you look at the in the current scenario, all those properties that we were thinking that we will try to understand, what were those properties? The geometry, the number of bonds, the shape, right? Yes, we do get some information about the geometry here and also the number of bonds, that is a secondary valence. Also the shape of octahedral complexes, but only in very few complexes, not in all the complexes, right? But the information about the color, magnetic properties, spectra, structure, stability, reactivity, high spin, low spin nature, splitting of d orbital, effect of ligand type, we do not have any information on all these properties by the Werner's theory. It was a great piece of work, but we do not get much information about this. Okay, so well, you can go through this and in our next short class, we'll be discussing the valence bond theory. All right. So with that, I'll be stopping on this point over here, and next class we'll be discussing the valence bond theory.